Hi, I'm Brian Durand with Machine Vision Store. This is the third video in our series on computational imaging. In the first video, we had an introduction to computational imaging. In the second video, we looked at some of the components for this technology. In this video, we're taking a close look at the lighting necessary to build computational imaging systems. In computational imaging, we capture multiple images of an object. Each image is captured under slightly different conditions in order to gain new information about that object. We then combine those input images together to build a composite image. If we've done our job correctly in designing the system, that composite image will have more information and enable better results for the inspection system. That holds true whether we're using traditional image processing algorithms or AI.
Light is our most powerful tool for computational imaging. We can learn how an object reflects and absorbs light when the light is projected from different directions. We can see how an image interacts with different wavelengths and different intensities of light, and we can do this very quickly, fast enough to analyze objects in motion. The previous video looked at building a high dynamic range image by varying light intensity. In this video, we're going deeper. We'll see real examples of dynamically varying light wavelength and direction, and we'll take a close look at the hardware that enables these inspections. Consider the markers shown here. Each has a cap and rubber tip that indicates the ink color. Our task is to develop a vision system that counts the number of rubber tips present. We're going to assume the markers are scrambled, that they come in many colors, and we're not able to mount a light behind the markers. Maybe we could use a color camera? We would have to train the software on each tip color. That would be a pain, given the many possible colors. And white balance tends to shift over time. I'm not liking that. Does computational imaging have something to offer? Well, we could gain more information about the rubber tips by lighting them with different wavelengths of light. That information would help us differentiate tips from the marker body. Say, capture an image with red light, an image with green light, and an image with blue light. Perhaps we could combine those images to build a composite that shows the tips only. After all, our task is to count the rubber tips, not the markers. Here's a flowchart built using Zebra Aurora Design Assistant. For demonstration purposes, we load the red, green, and blue input images from files. Next, we do a little image processing to build the composite image and then count the rubber tips using the Model Finder tool. With the exception of the colored tips, the silver markers pretty much disappear. Here are the components we used to perform this magic. The LAMAC RGB dome light. We use the 150mm model, but it is also available in 120 and 80mm sizes. Or we could have used some multicolor bar lights for a larger field of view. These are available in lengths up to 600mm. We used the LAMAC IDMU light controller. We happen to use the 8-channel model, but it is also available with 4 channels. In fact, it can be expanded up to 40 channels, but we'll come back to that. We used a Bosler Ace 2 2.3 megapixel monochrome camera with a Schneider Citrine 23mm lens to capture images. And Zebra Aurora Design Assistant software is running on a Zebra EV7 processor. The LAMAC IDMU light controller is at the heart of many of our computational imaging solutions. The IDMU is an expandable light controller, stack modules together to independently control up to 40 LED lights. There are a variety of ways to control the IDMU. There is an add-on module that has a knob for adjusting any channel. The base unit has an Ethernet port for communicating with up to 4 devices. Use the Gigi Vision Genicam protocol to communicate with machine vision software, such as Zebra Design Assistant. Use the TCP/IP protocol for PLCs or robots. There is a free software app from LAMAC to manually configure the controller, or use Hypal software to automate setup. The IDMU controller supports 4 recipes, each having up to 8 steps in the sequence. Each step can include actions such as turning on light channels for a specified duration and setting the intensity of multiple lights. Controller I/O includes 8 inputs and 5 outputs. Use the inputs to select a recipe, Outputs can be used to trigger up to 4 cameras for coordinating with strobed illumination. Advancement to the next step in a sequence can be based on either an input signal or a precise internal timer. The IDMU base and expansion modules are available with either 4 or 8 light channels, and there is a new 4-channel model that can overdrive your lights for brighter illumination. Okay, let's look at another example of computational imaging. Instead of varying the light's wavelength, this time we're going to vary the light angle. Our challenge is to inspect film on a pudding cup. We want to find any pinholes in the film, a potential threat to human health. I want you to know that I purchased these pudding cups at the store and then intentionally used a pin to make 2 small holes in the film. They did not come this way. I put the holes in the brown ink areas just to make our task a little bit more challenging. Most people would never notice these holes. They're too small and there is too little contrast. There are 2 factors that make this task difficult. First, the film is undulating and randomly reflects light. Second, the assortment of ink colors make it impossible to find the holes by just binarizing the image. So what are we going to do? We're going to project light from 8 different directions. We'll capture 8 images. Let's slow that down so we can see what's happening. The ring light has 8 independent banks of LEDs. We cycle through them, one at a time. When processed using photometric stereo techniques, we see only the pinholes. How did we do that? We told Hypol's software what light was connected to the IDMU controller. We chose one of the 6 algorithms available, enabled the Hypol contrast enhancement feature, then clicked the Send button. The resulting image can then easily be processed using a blob algorithm to find the pinholes.
In this video series, we learned what computational imaging is and looked at the components necessary to build a system. We then did a deeper dive into the lighting components, key to the success of any imaging project. We saw an example of varying light wavelength and a varying light projection angle.
If you would like our help designing a vision system or would like us to test your sample parts in our lab, please contact us today.